Okay, and then we have diffraction. And diffraction is when a wave passes either between and through an opening or around a corner. And once it gets past that corner and once it gets to that opening, it starts to bend around the edges. It starts to curve around the edges. Basically, it starts to spread out. And what this tells us then is that it's not going to go straight past it. It's actually going to go past it and then spread around behind it. It's why you can hear a lot of time. You can hear sound even though you're outside of a room. There's some reflection there, but there's also a lot of diffraction that takes place. If you ever turn a light on in a room and crack the door into like a darkened room, and you watch how that light comes through the door, you actually see it spread out into a cone shape as it enters that dark room, because the light is diffracting, it's bending as it travels through that opening. And the amount of diffraction is related to the size of the wave relative to the size of the opening. So if the wavelength is much smaller than the obstacle, then there's not going to be any diffraction. And that's why for instance, light, if you open up a door all the way, there's not going to be really any diffraction, because the doorway relative to the wavelength of the light is very, very small. It's why if you're out in the hallway, you can hear sound because the sound waves are much longer than the light waves. Okay, here's a couple images of it. And so you can see that as the light wave passes through, it doesn't just travel straight through. It starts to spread out in all directions. And notice here at the bottom, notice the difference between A up here and this one down here at the bottom with the large aperture. You can notice the difference in the amount of curvature. There's much more curvature here with the smaller aperture than there is down here with the larger aperture because of the relative size of the wavelength and the actual aperture itself. But it's not just openings. You can see here at B we have just an edge, and so instead of just traveling straight through, once it gets past that edge, the wave starts to curve around that edge as well, and that's diffraction. Okay, and then the last kind of two behaviors of waves have to do with how waves interact with each other rather than with their surroundings, and particularly how they interact when they come across other waves in the same medium. And so we'll start with the principle of superposition, and essentially it's just kind of a fancy name to say that the wave that you're going to see is going to be the sum of the two waves that are meeting. So as two waves travel in the same medium towards each other and they meet, they're going to pass through each other. But remember that wave is really just energy being transferred through the medium. And so if the two crests of waves meet at the same point, that's a lot of energy. All of that energy is at that single point. And so what's going to happen is the amplitude of the displacement at that point is going to be the sum of the two waves' amplitudes. And so they're going to add together. If if two waves meet each other and it's a crest and a trough, then you have positive energy and you have negative energy. And when those cross, they're going to cancel each other out, so you're going to have a much smaller wave. But one of the most important parts of this idea of superposition, waves meeting each other in a medium, is that as they pass by each other, they do not change each other. They're simply passing through. They don't affect the other wave. And so once they've passed through each other, they continue on their way completely unaffected. After they've passed through each other, their amplitudes return to normal and they continue on with the same speed, same frequency, same energy as they had before the interaction. And this principle of superposition really just mathematically relates what's going on in what we call interference. And that's when we have the superposition of multiple waves. And as I just mentioned, if you have a crest and a trough that meet, the resultant wave is going to be smaller than the two original waves. This is what we call destructive interference. Okay? The resultant wave is smaller. Now, if you have perfect destructive interference, that's when the crest and the trough have identical amplitudes, or the magnitude of the displacements are the same, but in opposite directions. So you'd have a wave with an amplitude of 5 meters and with a crest of 5 meters, and another one with a trough of -5 meters, and they meet. The net wave that you would see is going to be 0. That doesn't mean that the energy is gone or this disappeared. It just means that at that particular point in time, as they're passing through each other, the energies cancel each other out as it relates to the amplitude. And then constructive interference is when both waves have displacements in the same direction when they meet. So crest and crest, trough and trough. And the resulting wave in constructive interference is larger than either of the two waves individually. Okay, so here we have this pulse 1 on the left is traveling from left to right. The one on the right is traveling from right to left. When they meet, these two crests here and here are going to meet, and this resultant wave is going to be, if this is 1 meter and this is 1 meter, this resulting wave that you're going to see is going to be 2 meters. Now, the dotted lines are just there to show you the original waves, but you're not going to see those. What you would actually see is this particular wave right here, this this wave in the middle. That's what you're actually going to see. You're not going to see the resultant waves until they pass through each other. Now, once they've passed through each other, they're going to be back to normal. And actually, here you can see this one's not going to be 2, but here we go. This one down here is going to be twice. So it's going to be 2 meters because there the two waves are completely overlapping. Here they've just started to overlap, and so it's not quite double the 2. But once they've passed through each other, each of those waves is going to continue on their way completely unaffected by the encounter. Okay, here we have two pulses that are in opposite displacements. So we have a pulse that has a positive displacement at the top and a pulse that has a negative displacement at the bottom. As they start to interact with each other, this is what you're going to see. It's going to be slightly different from the two pulses. Once the two pulses are completely lined up, you're not going to see anything. There's still going to be 0 displacement of the medium. So this blue line represents what you would actually see. Then, once they're done, you would see, here's our pulse 2. It's going to continue traveling to the left. Our pulse 1 is going to continue traveling to the right. And again, they're completely unaffected by the encounter. It's only when they're on top of each other that you see the difference. It's pretty clear to see when you have waves in a string and you're really only working in 2 dimensions. When you start to work with things like sound waves or water waves that are spreading out 360 degrees, your interference patterns start to get a little more complex. And so here, it's kind of tough to see because you've got a lot of things going on, but essentially you have 2 sources of waves, and we can call them water waves, you can call them sound waves, doesn't really matter. But the idea is that you have 2 sources of waves, and if you look really closely you can see source 1 on the left. Those waves are represented by these blue lines. So the crests of those waves are spreading out in 360 degrees. We're showing them with wave fronts, which is what those lines are. The source on the right is using black lines to represent their wave fronts. And so these waves are spreading out and you're getting what we call interference patterns. And the interference pattern is this alternating series of constructive and destructive interference at different points. And these 2 black dots here, this one up at the top, first of all, if you look very closely, you can see that there's a crest, a blue crest here, and there's a black crest here that are meeting. And so what that means is that the wave there is undergoing constructive interference, and so it's going to be stronger. If this was if these were sound waves, at this point you would hear a much louder tone because there's constructive interference, and so the 2 sound waves are basically increasing each other. They're adding energy to each other, and so there's a louder sound there. Now down here at the bottom, this bottom circle, you have a black crest, but it's occurring right halfway in between 2 blue crests, which would be the trough. And so you have a crest and a trough. And so this bottom black dot here is an area where there's perfect destructive interference. And so again, if we're talking about sound, perfect destructive interference would result in silence. So the thing that we would observe would be silence at this point. And so you can see that if a person was to kind of walk across, if this was in a room, if they were to walk across the room, they would see a series of, there's destructive interference, here's constructive interference, here's destructive interference here, here's constructive interference here, here's destructive interference here, here's constructive interference here. So you can see there's all of these points where there's constructive interference, and then there's just as many points where there's destructive interference. And this is what we call our interference pattern. And we can measure it by testing it, by turning on the 2 sources and walking around and seeing where there's constructive and destructive interference. We can also calculate it, because the whether or not it will be constructive or destructive is directly related to the wavelength and how far you are from each source. If the difference in distance from the sources is a whole number multiple of the wavelength, then they're going to be in phase. So the interference will be constructive if the path length differs by a whole number integer of the wavelength. And so what that means is if we come back to this particular diagram, let's change our color. From source 1 to this point right here, the distance is 2 wavelengths. From source 2 to this point, the distance is 3 wavelengths. And so if so what you have is source 2, the path length difference here is a whole number integer. And so this is 2 wavelengths here. So we'll call it 2 lambda. Whoops. Okay, this is 2 lambda, whatever the wavelength is, and we're assuming the same wavelength for this one. This path length is 3 lambda, 3 times the wavelength. And so the path length difference is 1 lambda. It's 1 times the wavelength. If the path length is different by a half a wavelength, or any number plus 0.5, so 0.5, 1.5, 2.5, 3.5, then you're going to have fully destructive interference. And this path length difference here is this distance right here. Okay, so if this distance and this distance are the same, the path length difference is this section down here. There's a 90-degree angle right there. The other aspect, so then with that one, let's look at another one. Let's find some destructive interference. Let's just find one. Okay, so here, up here at the top. So this is 1.5 wavelengths from S2. 1.5 wavelengths. It's 1, 2, 3 wavelengths from S1. And so the path length difference here is 1.5 wavelengths, and so that means that you're going to have perfect destructive interference.